G'day all, welcome to another tube. So today we're going to be looking at a little introduction to the Shunting Yard Algorithm. This is an excellent algorithm, and later on we'll code it, probably in C#. I'm thinking for our calculator tubes. Anyway, let's get started. So the way that we write mathematical expressions is called infix notation, and operators have a precedence and brackets override this precedence. Many programs like scripting languages, your spreadsheets, compilers and calculators require the parsing of expressions. And a really good way to do this is to convert the expressions from infix into an intermediate format that the computer can understand really easily. And we're going to be using a very popular intermediate format called reverse Polish notation. Okay, so the Shunting Yard algorithm actually converts the expressions from infix into reverse Polish. That's kind of the point of it. And it's not a basic algorithm like your bubble sort or a string search. It's pretty fiddly, and it's quite advanced. It's got a stack and a queue and an array all kind of combined into the same algorithm. But it's really worth looking at. Very interesting stuff. Anyway, first of all, we're going to pay a bit of a tribute to the man that invented it himself. Yeah, I don't like to just introduce an algorithm like this sort of without mentioning that actually it came from somebody's head. Somebody sat down and figured it out one day. Somebody very clever. After that, we'll look at some expressions, or an expression in infix notation, just to make sure we're all on the same page. And then we'll look at the same expression in reverse Polish. And finally, we'll look at a pseudocode version and a step-by-step demo of the Shunting Yard algorithm itself, so that we can see how it converts infix to reverse Polish. And we'll code in a separate tube. Okay, here he is, the man himself, Mr. Edsger Dijkstra. I think that's how you pronounce it anyway. So if you've ever tried to program software to parse mathematical expressions, you might have been surprised at just how difficult it is. It's not easy. But thankfully there was a guy called Edsger Dijkstra, and thankfully also he was an indisputable genius. This is him over here, by the by. And he was also a computer scientist. Yeah, one of the biggest names in modern computer scientist circles, really. This guy invented semaphores for concurrent programming, Dijkstra's shortest path algorithm, the Shunting Yard algorithm, which we're looking at here, and even reverse Polish itself. Good stuff. Genius. Very cool. Okay, so a few terms before we start. We've got tokens. We're going to be splitting the expressions into little pieces called tokens, and a token can be a number, an operator, or any other distinct mathematical symbol, like a function or variable name. We've got operators. This is any mathematical symbol used to represent an operation. Yeah, plus, minus, multiply. We know what the operators are. We've got a stack, and this is a little data structure in computer science. So if you're not familiar with the LIFO data structure called the stack, have a look on Wikipedia. And we've got a queue, which is another data structure. This is a FIFO data structure, first in, first out. And if you're not familiar with queues, have a look on Wikipedia. Good stuff. Okay, so infix notation. This stuff is going to be, you know, really well known to basically everybody on the planet after the 3rd grade at school. But operators have a precedence, and operations in brackets are to be performed first, then division and multiplication, followed by addition and subtraction. We all know these rules, but let's just go through it so we can see what's happening. Right here I've got a little infix notation expression. I'm trying to set the variable I to whatever this expression evaluates to. And I put a semicolon on the end for some reason. I'm not sure what language I'm trying to program here, but I just thought it would be good to put a semicolon on the end. Anyway, we want to evaluate this expression, this infix notation expression. So what are we going to do? Well, we're all really familiar with infix notation, and with a quick glance we can see that there's brackets. So we have to evaluate the brackets first. The 7 minus 3 should be performed first. So we go 7 minus 3 equals 4. Then we do the division, since division overrides, or division has a higher precedence than the addition. So we do the division next. 24 divided by 4, and the 4 was our result from the 7 minus 3. 24 over 4 gives us 6. And finally we add the 9 to that result to get 15. And that, 15, is what the variable I is going to be set to when we evaluate that expression in infix notation. Okay, so although that seems perfectly natural to us, we've been doing infix notation expressions for a long time. It actually requires a scanning of the expression for brackets and an ordering of all of the operations by precedence, and it's complicated stuff. Yeah, so computers don't particularly like doing that sort of thing, scanning backwards and forwards and ordering brackets, and they don't like doing that. So we've got this format, reverse Polish, another way to write an expression. Before we can have our calculators or our programs calculate expressions, we've got to convert them into this intermediate notation. And in this notation, reverse Polish, there's no operator precedence and there's no brackets either. Everything happens when the computer reads the operations. Yeah, in that order. Okay, so expressions are passed from left to right. By passed, I should say this too. Parsing just means to sort of read and understand. So expressions are read from left to right. Yeah, I don't know how common a term that is, but we're parsing expressions here basically. We're reading them. Anyway, expressions are read from left to right. Each time a number or operand is read, we push it to a stack. Each time an operator comes up, we pop the required operands from the stack, we perform the operation, and we push the result back to the stack. We'll see this in just a second. And this is not the Shunting Yard algorithm. This is just how you figure out what a reverse Polish notation expression means. Anyway, we're finished when there's no more tokens left to read, and the final number on the stack is the result of the expression. That's good. Let's have a bit of a look. So this is the exact same expression as before, only this time it's not in infix notation, it's in reverse Polish. This is going to look a little weird if you've not seen it before, but yeah, this is exactly the same expression. I put commas in to separate the tokens here. Yeah. So this happens to be the exact output of the shunting yard that we're going to look at when we give it the infix expression from earlier. Anyway, this is how you would read this this reverse Polish expression. The first token is a number, so we set up a little stack. Yeah, I don't know if I mentioned that, but we set up a little stack. The first token is a number, so we push it to the stack. The next token is a number, so we push it to the stack. The next token is a number, so we push it to the stack. And of course 3 is a number as well, so we push that to the stack. After that we get an operator, the minus symbol. And the minus symbol takes 2 operands. We've programmed that in our algorithm somewhere. And so we know to pop 2 operands off the top of the stack, perform the minus, and push the result back to the stack. So 7 minus 3, those were the 2 operands. 7 minus 3 gives us 4. We push the result back to the stack. Okay, the next token is also an operator. This is divide, and that takes 2 operands as well. So we pop the 24 and the 4 from the stack. We perform the division to get 6, and we push that 6 back to the stack. And finally, we've got the addition. So addition is an operator as well. We pop the 2 values from the stack. We figure out the result of the addition, which is 15, and we push that back to the stack. And you'll see that really all we're doing is pushing all of the numbers to the stack, and each time an operator comes up, we pop a few operands from the stack and push the result back. That's all there is to reading a reverse Polish notation expression, and I'm sure you can see it's really, really easy for computers to evaluate these expressions. You'll also note that this is exactly the same answer that we got from our infix expression. Yeah, reverse Polish has to give the same answer. Otherwise it wouldn't be a very useful way to write an expression. Okay, that's good. So at this point we're done. 15 is the answer. Good stuff. Okay, so on to the algorithm itself. The Shunting Yard algorithm, like we just said, converts from infix to that reverse Polish notation that we just saw, so that a computer can just zoom from left to right and evaluate the result of the expression really, really quickly. Okay, so you'll need, I've written this out as a recipe for some reason. It's pretty good. Good recipe. You're going to need 1 stack for operators, 1 queue for the output, 1 array or other list of tokens. We're going to look also when we come to program this at another function called tokenize. which is just going to read through an infix expression and split it up into tokens. But yeah, you're going to need some tokens to convert in infix notation. So that's what that is, one array. Okay, so the basis of the algorithm, it's pretty much like this. This is just pseudocode. So while there are tokens to read, we read a token. If it's a number, we add it to the queue, and we're done. If it's an operator, then while there's an operator on top of the stack with a greater precedence, we pop operators from the stack onto the output queue. And finally, once we're done doing that, we push the current operator onto the stack. So that's all a little loop there to make sure that we're doing our operations in the right order. This is going to yeah, figure out how to do the divides and the multiplies before the additions and subtractions. Pretty good. Okay, if there's a left bracket, we don't count brackets as operators in the shunting yard. We count them as, you know, separate entities. So if the token that we read was a left bracket, we push it onto the stack. This is sometimes called the operator stack. Yeah, because we push all of the operators onto this stack, and we push brackets on there as well. If it's a right bracket, however, then while there's not a left bracket on top of the stack, we pop operators from the stack onto the output queue. And after that, we pop the left bracket, but we don't push it onto the stack. We just discard it, throw it away. Don't need it. And then finally, once we're done doing all of that, once we're done reading all of the tokens, while there's operators on the stack, we pop them onto the output queue. And that's all there is to it. I don't know how much sense that makes, you know, just reading through it. So, yeah, I thought we'd have a bit of a look at it. Good. Here we go. So here's my array, my list of tokens in infix notation. Read it from the 9 down here upwards. So 9 plus 24 divided by, open brackets, 7 minus 3, close brackets. That's the same infix notation expression from earlier. I've got an operator stack just here, which is going to fill up from the bottom to the top. And I've got my output queue just here, which is also going to fill up from the bottom to the top. Okay, let's get started. So, the first thing that we do, while there are tokens to read, we read a token. We read this 9 down here. If it's a number, add it to the queue. So there it is. We put it on the queue, easy as that. Then we read another token, so we don't have to do anything after that. Yeah, we read another token. If it's an operator, and it is, it's the addition operator, then while there's an operator on top of the stack with a greater precedence, we have to pop the operators off the stack. But the stack is empty at the moment, so there's no operators with greater precedence, so we can proceed to the next line, which is just push the operator to the stack. There it goes. Alrighty, then we read a token. It's a 24. That's a number, so we add it to the queue. We read another token. This is an operator, the division symbol. And while there's an operator on top of the stack with a greater precedence, we're supposed to pop operators from the stack. But the only operator on the stack is a plus, and plus has less precedence than divide. You'll find when you write your shunting yard algorithm that you actually get to choose the precedence of all of the operators. Yeah, you can swap plus and divide's precedence if you like. If you want to confuse people. Okay, that's good. Plus has less anyway, so we don't pop anything off the stack. Instead, we push the current operator, which is the divide, to the stack. Okay, then we read a token. If it's a left bracket, and it is now, we push it onto the stack. There it is. Then we read a token. If it's a number, we add it to the queue, so we put it over here. That's the 7. Then we've got another operator. This is a minus operator. And while there's an operator on top of the stack with greater precedence, we're supposed to pop operators from the stack. But the bracket just here is not an operator, so we don't pop anything from the stack. Instead, we just push the current operator, the minus symbol, to the stack. Yeah, if that bracket wasn't there, and that divide was the top operator on the stack, then we would have popped the divide onto the output queue to make sure that it gets done first. That's good. Good. Okay, then we read another token. Would you believe it? And we read this 3 just here. So that's a number. We put it onto the output queue. And finally, we read the last token, the close bracket. So if it's a right bracket, then while there's not a left bracket at the top of the output stack, we pop operators from the stack onto the output queue. So this is making sure that the operations inside the brackets are done first. There we go. So we just popped that minus symbol from the operator stack and put it onto the output queue. Okay, while there's not a left bracket on top of the stack, so there is a left bracket on top of the stack now, but straight after we've done that, we pop that left bracket to oblivion. Yeah, we don't need brackets in reverse Polish, so we just pop it away. Okay, and now there's no more tokens to read. We've just read the last token in our infix expression, and we jump down to the end, which is another little loop. While there's operators on the stack, pop them onto the output queue. So obviously a stack goes in the reverse order that we put the operators on there. So first we pop the division, then we'll pop the addition, and hey presto, we're done. Amazing. So the output queue now contains the tokens in reverse Polish order. Absolutely amazing. So it's a queue. It's going to be read from the bottom to the top. And you also might note that it's exactly the same as the reverse Polish that we just had a look at. So 9, 24, 7, 3, minus, divide, and plus is the exact reverse Polish expression that we just looked at. Okay, there is a few additional things which really come up when you actually come to program this. And yeah, let's just have a bit of a talk through a few of them. So if you run out of tokens on the stack while you're searching for a left bracket, there's been mismatched brackets. If you find any brackets whilst you're doing your final operator popping, then you've got mismatched parentheses. I'm not sure why I did parentheses there and brackets up there, but pretty good. Okay, so the algorithm is also capable of dealing with functions and comma-separated parameters. Yeah, it is. It's extremely flexible, really. I don't know if the one that we code will do functions, but it's not too difficult. Maybe we will. I don't know. Operators have a notion of associativity, left or right. Yeah, they do. So yeah, we will actually incorporate that as well in our one, since you really can't you really can't make even a basic shunting yard without incorporating this associativity of operators. So we'll go through that. It's not restricted to numerical expressions. Oh, this is beautiful. This is amazing, really. This algorithm is just as comfortable working with string expressions or logical algebra and operations. It can do, expressions on basically anything. Anything at all, really. It can parse and transform into reverse Polish. Just crazy. Very, very good, though. Also big... Oh, yeah. Yeah, this... You never even think of this before you come to write an expression parser in some language. But the binary subtraction operator and the unary negative symbol look exactly the same, but in this context, they're not. One of them takes 2 parameters, so, subtraction takes 2 parameters, 5 minus 12. And the other one only takes 1 parameter, so negative 5. And you need to know, like we just said before, when you're evaluating a reverse Polish expression, you need to know how many operators to pop from the stack, how many parameters to pop from the stack. Yeah, so you need to know whether it's a minus symbol or just a unary negative symbol. Anyway, we'll go through this in the example. Okay, so we will code a shunting yard, but we won't do it today. That's about all I wanted to say, so thank you for listening. See you later.